yeah.
Our last speaker for this very interesting day is Ramos, and he's going to speak about an AI-enhanced approach to the unimodality conjecture. Take it away.
Yes, thank you, Sandra, for being primary organizer for all of this.
You'll organize it too.
Yeah, I think this was like kind of a brilliant bit of organizing, because what I'm going to talk about is essentially like the intersection of the previous two talks. So today we're going to talk about this thing called the unimodality conjecture, and in particular, some really awesome results that we got using machine assistance for it. Okay, so I probably don't need to say this, but for a given graph G, an independent set, we mean a set of vertices which are pairwise non-adjacent. The independent sequence is then the integer sequence A1 up to A alpha, where AI is the number of independent sets of size I, and alpha is the independent number of the graph. We call it rather the independence number of the graph. Okay, so it is a famous fact that this sequence is unimodal. In fact, stronger than that is what's called real rooted. If G is a claw-free graph, so this was proven by Chodnovsky and Seymour, although like weaker versions of this theorem had existed before that. And it was proven by Alavi, Malde, Schwenk, and Erdös that this is extremely, extremely untrue for general graphs. So what do I mean by extremely untrue? Let me try to make this precise. So here's a theorem. Let G be a graph with independent sequence A1 to A alpha, and let pi G be a permutation which essentially takes the independent sequence and reorganizes it in increased order. Then the assignment, which sends G to pi G, is a surjection from the set of graphs to the set of all possible permutations. Okay. So what this says is that if you allow me to work with any graph, like the independent sequence can essentially, in terms of like the relative orders of its elements, can look virtually like anything. So this is like the most non-unimodal that you can possibly be. However, in that same paper, it was conjectured that the independent sequence of trees should be unimodal. So once again, we know it's true for claw-free graphs, and the tree unimodality conjecture postulates that it is going to be true for trees as well. So you can think of that as like two extremes, right? Because claw-free, you have no induced claws, and then tree is like everything is a claw, right? So it's like these are two extremes in some sense, and what it's saying is at the extremes you have unimodality, but in the middle, like pretty much anything goes.
What is a claw?
A claw, good question. So when I say a claw, I mean a subgraph that looks like this, but specifically, an induced subgraph that looks like this. So in other words, I want to find this structure in my graph, but like they're not secretly the edges here, or here.
Okay.
Yeah.
So it's a star of size whatever.
Yeah, that's right. But induced. Yeah. Okay. So this conjecture was later strengthened by Galvin and others to state that the independent sequence of trees should be log-concave. So this is, you might call the strong tree unimodality conjecture. If G is a tree with independent sequence A1 to A alpha, this sequence is log-concave in that for all I, AI squared is bigger than AI minus 1 times AI plus 1. So this condition in the kind of center of the conjecture statement here is what's called log-concavity. So called because if you take the logarithm of both sides here, that's concavity. Right, the 2 comes down, divide both sides. And log-concavity, just like of sequences, is something that's really very hot right now because of like really deep connections between it and like geometry and matroid stuff. Like June just won a field medal essentially for proving chromatic numbers were log-concave and all this type of stuff. So, okay, chromatic polynomials, I should say. Okay, so this is the strong tree unimodality. Now, this stronger version of the conjecture stood for decades and in fact was verified computationally for all trees with at most 25 vertices. In 2023, however, Kadrawi and Levit, the same Levit from the previous talk, prove that there are exactly 2 trees on 26 vertices that fail to be log-concave. Okay. So if we had just taken one step further, we potentially would have found these counterexamples. Now, the breakage of the log-concavity condition, remember the log-concavity condition in respect to like indices of the sequence. So the breakage happens at the index I is equal to 13, which is the penultimate in this case point in the sequence. And note that there are about 160,000 isomorphism classes of trees on 26 vertices, and they proved in this paper through exhaustive computer search that these are the only 2 counterexamples for log-concavity. And they look like this. These are the 2 trees on 26 vertices whose independent sequence fails to be log-concave. Notice that they look very similar. Okay. So now, these 2 trees were discovered through ad hoc reductions and exhaustive computer search, as said. In fact, it was shown that each of these fall into 2 natural families of trees, and in all cases, I will show the families in a second, but in all cases, the breakage happens at the index, which is exactly half the number of vertices, and either 1 or 2 below the top index alpha. So these are the 2 families. So what I'm saying is like all trees in these 2 families will fail to have log-concavity in their independence sequence, and the breakage happens like pretty much at the top of the sequence in both cases.
Wait, so this extends beyond 26?
Oh yeah.
Anything
So and for any k at least 4.
Okay. Yes.
Yeah. Mm-hmm. Now, importantly, again, it's like they had the 2 kind of 26 vertex examples, and then they were like, hey, you know, in some sense, if we just add more things to the middle, like it doesn't change the fact that the breakage is happening. So, okay. All right. Following this, in February of 2025, Galvin produced a family of examples with a parameter t, which for t greater than or equal to 4 has a single breakage in the independent sequence, which happens at about half the number of vertices asymptotically. As the number of vertices goes to infinity, the index of this breakage happens further and further from the independence number. So it's like in this family, the point of this work was to be like, hey, those counterexamples I just showed you on the previous slide, the breakage always happens at the top. So the natural question is, can breakage only ever happen at the top? So Galvin is like, no, it can pretty much happen any finite distance from the top, okay? And the trees look like this. This is the family. So you have a root with 3 children, or sorry, rather t children, and each one of those t children has this kind of repeated edge t times. Okay. So if you compute the independent sequence here, you can prove that there is a breakage, and that breakage is happening further and further from the independence number as t goes to
You mean it's not in the middle?
No. So, well, okay, so the independence number is increasing as well. Just to be clear, the point is like the independence number is going to infinity with t. And where the breakage is happening can be made to happen like essentially for any fixed k, you can make it happen k away from the top.
Oh,
Yeah.
yes.
So it's not the case that this construction is like, oh, I can find a breakage at half of the independence number, right? At half of the sequence, right? It's happening at a fixed fixed index away from the sequence. Which is different. All right. So as of the beginnings of my project with Sunny, these were all of the known counterexamples to the log-concavity conjecture, and so I just want to point out a few important things. In all cases, the independent sequence is still unimodal, and this is still the case. We do not know whether the original tree unimodality conjecture is true or not. It's still open. In all cases, the breakage happens at exactly 1 index. So in all of the examples I just gave you, there is 1 breakage. In all cases, the breakage happens at an index which is either n over 2 on the nose, or it turns out close to n over 2 in like a precise asymptotic sense. And all of these counterexamples have a very similar vibe. So a root connected to some number of vertices, each of which have an equal or near equal number of children, and all of those children are paths. So just to explain what I mean here. It's like, for instance, if you look at this, right? Root at the top, some number of children, in this case 3. And then each one of those has grandchildren, but think of the grandchildren being like a path rather than like a single vertex. And the same with the Galvin example. Okay, the exact same. Okay. All right, so this was like as of the beginnings of the project here. But now since this project has appeared in print, there's been a flurry of activity. So most significantly, Bautista Ramos, no relation, has given a family of trees where log-concavity can be made to break at an arbitrary many number of indices, right? So it's not just like, oh, there's only ever one breakage. It can be made to break any number of times in the sequence, either consecutively or non-consecutively. These families are obtained by taking many copies of the Galvin counterexample and connecting them to a common root. So again, it's like everything is just building off of those original 2 counterexamples. They all look very similar. It's like these 2 work, so let's just take the 2 that work and just modify them in minor ways and be like, aha, look, counterexample. Now, in terms of this like many breakages phenomenon, the smallest of their examples with at least 2 breakages has about 180 vertices. So this is not something that's easy to construct, it seems.
This is still all like computational?
So they, as I said, they have an explicit construction, which is basically take many copies of the Galvin thing and then like glue them together. And then they just prove explicitly that the independent sequence breaks at some number of indices. Through all of these works, all new families of counterexamples are built from the original few families by gluing things together. And now I just want to be clear, it is not the case that these types of gluing or sprouting operations will always cause log-concavity to break. In particular, we don't have a meaningful structure theory for why log-concavity breaks. It's not the case that if you take a counterexample and you glue it to another counterexample, the result is always a counterexample. So like it's like, again, thus far, virtually everything that's been done is very ad hoc. Okay, so now I promised that there'd be some kind of machine learning or AI in this talk, so let's switch gears to that. So for this project, we hope to use Machine Assistant to produce more and more examples of trees which fail to be log-concave. We used PatternBoost, which is an architecture developed by Charton, Ellenberg, Wagner, and Williamson. Francois Charton, Jordan Ellenberg, Adam Wagner, and Geordi Williamson. This architecture involves a loop of a more classical local phase, where an algorithm optimizes provided inputs, and a global phase where a machine is trained based off the optimized examples coming from the local phase, and produces many samples based off this training to be the next generation's inputs for the local phase. So before we go over the process in like more detail, we can summarize as follows. Step 1, decide on a means of representing the objects that you are trying to optimize, so in our case trees, as a string of tokens, and decide on a scoring function for which higher scores means better solutions for whatever problem you're working. That's step 1. Step 2, start with some number, in our case 50,000, of randomly generated objects. Run each one of these samples through some optimization algorithm whose only purpose is to improve the score, right? So I'm not talking about some sophisticated like computer science here, like a greedy whatever, which is basically what we're going to be doing. Just anything that improves the score. We call this the local phase. Send all of these improved samples to a machine learning agent to be used as training data. Once it is fully trained, prompt the agent to produce some number of new samples, in this case about 100,000. We call this the global phase. Send each of these samples back to the optimization algorithm and keep the top scores to send back to the machine agent, and you keep doing this generation over generation. That's the idea. So it looks like that. It's just like a graphical represent.
What is the score you are interested in?
So that's what we're going to get to. To start, we have to determine 3 things. What is our scoring function? What is the most efficient way to encode our trees to be understood by the machine? And what is our optimization algorithm? Those are the three things that we need to input here. So step one, the first is the scoring function. We define the score of any input tree to be the following. So SI is equal to AI plus 1 times AI minus AI squared for a fixed chosen index I. Yes. Thank you. This should be AI minus 1. So observe that a tree fails to be log-concave at the index I if and only if the score is positive. Right? By definition of the log-concavity condition. Okay. So now, because of the existing history of counterexamples, we initially focused our attention on the specific scoring function Sn/2, where n is the number of vertices of the input. Again, all previous known counterexamples, breakage happened at n/2 or near n/2. So now, I will say there was a work that came out after ours, which used our kind of architecture, where instead of looking at independence numbers of trees, they looked at dominating numbers of trees. And for them, instead of like fixing and looking at n/2, what they did was they looked at distances from the domination number. So the score was defined, I mean, it's the same kind of formula here, but where I was chosen to be like the domination number minus 1 or something. And they had success. Okay, so first of all, one thing that might give some pause is the question of whether it is at all practical for this to be our scoring function. After all, computation of independent sequences is generally an extremely hard thing to do. It turns out for trees, the computation of the independent sequence could be done in no worse than O(n) time for exactly this recursion that was brought up in the previous talk, right? Because once you have this recursion, and the fact that you're working with a tree means there's no nonsense with cycles happening. So this is like a dynamic programming thing that you literally just start at the root vertex and propagate the information downwards and then pull it back up. So in other words, like our score function is like not hard actually. It's surprisingly not that bad to compute. And again, this recursion is just the observation that at each independent set either contains a vertex B or a. It's just the binomial coefficient recursion.
Very explicitly compute the sequence.
Yes. All right. So next we have to decide how to encode our trees. So an obvious way to do it is by flattening the adjacency matrix into a string, right? You get an adjacency matrix, and then you literally just take row by row, put the rows next to each other. Now that is a string of zeros and ones that represents your tree. This is inefficient at the very least because you do not need the entries of the matrix below the diagonal, right? Because it's symmetric. So okay, you're like, great, you know. When it comes to engineering, sometimes the difference between n squared and n squared over 2 is actually like a big deal. So it's like maybe that's the best we can do. But in fact, once again, for trees, we can do better. So even accounting for this diagonal issue, we can actually encode our trees in a much more space-efficient fashion by using proofer codes. So this code will uniquely express any vertex labeled tree, sorry, let's just say tree, with n vertices as a sequence on 1 to n of length n minus 2. So the encoding works as follows. So given a labeled tree, remove the smallest leaf and record the neighbor's label. And then repeat until you only have an edge left. So it looks something like this, right? So here's the tree. The smallest leaf is 1. It is connected to the vertex 2. So my code is 2 and that leaf is removed. All right, the smallest leaf is 3 and it's connected to 2. So we get here and so on. So now 2244 is the unique proofer code that corresponds with this labeled tree. Right? This is it. This is the bijective constructive proof of Cayley's formula, where it's like the number of labeled trees is n to the power n minus 2.
But the labeling will make it.
Yeah. So this is a great point. So proofer coding is an immensely elegant and importantly compact way to represent labeled tree as a string whose length is 2 less than the number of nodes. But there are drawbacks, as was just mentioned. Like The first is now we are forced to work with labeled trees rather than just abstract trees, right? And in terms of independence numbers, who cares about the labels? So like, and to be clear, like I said that there's about 160,000 isomorphism classes of trees on 26 vertices, for instance. What is 26 to the power 24? That is like astronomically bigger, right? So we are introducing a ton of noise into our into the space that we're working in. Moreover, and this is more subtle, is that the proof of code does not obviously represent the independence numbers of the trees. In other words, it's possible that this choice of representation will hide the independence sequence from the transformer during training, right? This is something that computer scientists care a lot about, and it might seem not a big deal, but it turns out to be a huge deal for a lot of these things, where it's like the representation of the thing that you're working with has a colossal potential impact on efficiency of anything you're doing, right? But what was incredible, and frankly not expected, I started with the proof of code because I was like, I want something efficient, let's just work with this, and then when it fails, we'll do better, and it just never failed, which was amazing, right? Our experiments revealed that the gains from the compactness of this representation actually outweighed all of the cons. So the fact that this representation only needs on order n space, actually the efficiency gains in terms of computation outweighed anything else. Now, the extra noise from the labels did manifest itself in a somewhat unexpected way, which I'll return to later. Okay, so our final most technical challenge will now be to decide on an optimization algorithm. Remember, our score is this weird thing in terms of like the product and the difference of independence numbers, right? That's how our scoring function was defined. And I need an algorithm that it takes in a tree and it spits out a tree for which that number is bigger. Okay, so given an input tree, choose a non-edge to add. Now, how do you make this choice? We'll talk about it a bit later, but choose a non-edge, right? Add that edge. Now, when you take a tree and you add an edge, you always create a unique cycle. Okay? So what I'm going to do is walk along that unique cycle and compute the score of the various trees obtained by removing one of the edges of that cycle. Replace the original T with the tree obtained in the prior step with the largest score bigger than the original score of T. We call this one single edge swap.
And if that was not,
then it's like, oops, that was a bad edge to try to add. So it's not counted as an edge swap, very importantly. And then the idea is we repeat this until some prescribed number of swaps has happened. Okay. So usually 10, actually. 10 was the kind of swap. So here's the kind of a pictorial representation. So suppose that path is my starting tree, and suppose I just chose to try to add the red edge. And then I'm like, okay, here's my triangle now that I've created, and you try to remove edges from this triangle, and it turns out that this particular tree has the biggest score, which is strictly bigger. All right, so a few questions remain. For instance, how do we select which edge to add? So there are a number of ways to do this, but we'll focus on two possible choices. The first choice is to add the edge each time completely around. Right? You have a list of the non-edges, and you're just like pick one uniformly at random. This option performed the best by far in terms of the results, but interestingly, only when n was sufficiently large. When n was below 35, this option performed worse than our second option. And well, let me just talk about what the second option was. Which the second option was to take all potential edges and sort them by the total degrees of their endpoints if they were to be added. Okay. In other words, like what I'm going to do is I'm going to look at all non-edges that I could possibly add to this tree, and I'm like, which one of these non-edges, if I added it, would create the vertex for this tree? And the reason that you might do this is because like now I'm adding in edges in a way that is designed to promote branching. Right? Because the resulting tree now suddenly is going to have a vertex of potentially large size. Promote branching.
Quick question. So
yes.
You're adding an edge, and then how do you choose which ones to remove?
So
just the ones that form the cycle?
Right. So when you add the edge to, because we're working with trees, when you add the edge, you always create a unique cycle. So you walk along that cycle, and then each edge you try to remove, and then you're like, okay, that's a tree. If I remove any edge from the cycle, I have a tree again. So remove the edge, you have a tree, computed score. And then go to the next edge, remove it, you have a tree, computed score, et cetera, et cetera. And you keep doing that until you find which edge do I need to remove to create the tree with the biggest score.
So at this point, there are potentially many local ways to change the tree and
Yes.
get something. Right?
Yes.
So that's one of them.
Yes, absolutely. Okay.
And then your second option was what?
So the second option here, it's like the non-edge that you add is specifically chosen to create the largest degree of a vertex possible. Does that make sense? Yeah. So the second option performed way better for smaller n, and the first option performed way better for larger n. And the difference here is stark. So like in the paper, we talk about this experiment that we ran where it's like, okay, we did the first option here, the choose the edge at random with 60 vertices. And after 5 generations, we found something like 40,000 unique counterexamples to log-concavity. Okay. If you do this option instead, we found something like 200. If you're expecting the word 1,000 to come out after that, it's not. 200 counterexamples to log-concavity. So it's like this performed considerably better. However, this generally did not find counterexamples when you were below 35 vertices. So like somehow this option actually did way, way better below about 35 vertices. Our best,
Is there an insight for this? Or?
So our best guess is essentially that like, and we'll talk about more about this, but it's like as the number of vertices gets higher and higher, when you look at the counterexamples we were finding, they look very close, pretty generic. Like the counterexamples we were finding for large n looked very, very diverse and essentially random. However, for small n, it's like it seems like again, the first instance where you even have counterexamples, there's 2 of 160,000 possible trees, right? So like for small n, it seems like an extremely needle in a haystack type phenomenon, whereas for large n, it seems more and more generic. So like the random choice here is doing better and better for large n, whereas this like very, very, very non-generic operation of like choosing the edge, which makes the biggest possible vertex, does better at the smaller degrees. Okay, so the next natural question is how many edge swaps should one perform on each tree? Remember, one edge swap is just one edge swap, and I said back then, I was like, we did 10. Where did that number come from? Okay, so the obvious choice is just to continue to do swaps until the score can no longer be increased, right? Just swap your heart out until you literally can no longer improve. This has 2 serious problems. Firstly, and most obviously, performing that many swaps becomes computationally untractable pretty quickly. Remember, to perform even a single swap requires you compute the score function for O of n many trees, right? Because like in the worst case, you added an edge, which just turns the tree into one big cycle, right? And you go along that cycle and you're removing every single possible edge along that cycle. So like somehow, if you try to do every possible swap that you can do, you're like really ramping up the amount of computation you're doing. But secondly, recall that our objective is to produce any tree with a positive score, right? I'm trying to produce counterexamples. I'm not trying to produce the most counterexample-y of counterexamples, right? So like performing too many swaps runs the risk of missing tons of counterexamples by optimizing the amount of existence. For instance, the following is a histogram of the final outputs of the machine when we tried to edge swap to exhaustion. Okay? So this is a histogram. So here's what happened. So we're like, okay, we're young and naive. Optimize, go. And then we looked at the output, and here's the histogram output. And what the machine was like, okay, I only care about 2 trees. I care about this, and I care about this. So it's like, what happened here was that the machine started to output two isomorphism classes of trees, one of which is notably not a counterexample to the left of 0. And this one over here, which is a counterexample, but again, it's only one isomorphism class of tree here. Now, because this is going to become a recurring pattern, does anybody want to guess what this is? What tree this is? Again, not a counterexample, it's just to the left of 0. It's the path. Right? Great. And now, this will come up over and over and over again. The machine constantly, no matter, well, not quite no matter what we did, but like the machine consistently became obsessed with the path. And you're like, oh, maybe it's a local, maybe it's some kind of local extrema for your optimization algorithm. No, it's not. Okay? It's not a local extrema. There's a path, and that is one genuine improvement upon it. But for some reason, the machine every single time would eventually just be like, "Hey, have you heard about this thing called the path? I don't know if you heard about it. It's pretty cool." But the point being is like when we actually went through the outputs and looked generation over generation, there were tons of counterexamples here. But it was basically like counterexample, and then it's like, oh, well, it's great that the score is positive, but why don't you do 100,000 more edge swaps? And then all of a sudden you end up over here. Okay. All right. In the experiment captured in this histogram, the machine's final output consisted of 5 total trees on 38 vertices. One of these trees was the path graph, which it outputted various relabelings of 40,000 times. The other 4 graphs had positive scores around 10,000 each and was outputted about 30,000. So it wasn't quite correct to say there was only one, but it ultimately ended up only being 4. In contrast to this, when we reran these experiments while only changing the number of edge swaps to 10 total, like once you've done 10, just stop, we came away with hundreds of different counters. So that concludes our outline of the local phase. Now, let's take a few moments to discuss the global phase. I'm not going to go into detail with this in terms of the machine learning. The PatternBoost architecture uses an out-of-the-box transformer model for its machine agent. So a transformer is a machine agent that, from an input string, attempts to guess the most likely next token based on a corpus it was trained from. Okay. Importantly, the transformer model was first introduced the idea of what's called attention, which for machine learningologists is like pretty much the biggest thing since sliced bread. The idea is like the following. It's like, okay, think about when you're writing emails on Gmail or whatever, and you start typing a sentence, and then it gives you like the suggested, here's probably what the next few words are, right? To do that, it's not really quite enough to just know what the current word I just typed is. You have to not only know what the current word I just typed is, but you also have to know the context. You have to, but more than just the context, you have to know that certain words leading up to the word that I just typed were kind of more important in the English language than other words. So this is the idea of attention, which is like it trains itself to know what parts of the previous what's been written are kind of the more critical parts to what the ultimate thing that's being conveyed is. Just like with any machine learning things, there's no way to tell precisely what aspects of its inputs that the transformer chooses to pay attention to. Is kind of one of the key, I mean, this isn't very, very active realm of research for machine learningologists, right? Where it's like the machine gets better and better, and it's like, oh, cool, so it must be paying attention to something. But it is generally impossible to know what exactly it is paying attention to. Sometimes you can tease it out, but the vast majority of the time you cannot. And this is kind of, yeah. Okay, anyway, so that was just like an extremely brief, this is what a transformer is, and this is the machine object that's being used in what we're doing. All right, so once we were able to code up all of the above and begin running things on GPUs, we began finding counterexamples to log-concavity pretty much at will. It wasn't even, it was one of these things where it's like, at first we ran it on our local machines, right? And it took us weeks of just like engineering like, oh, let's swap the order of these two if statements to make it run a little bit faster, and like dumb engineering things. And then finally, after like a month, we found the original two counterexamples of 26 vertices. And I was like, this is so great. I'm so happy. This is good enough proof of concept to convince the powers that be that I should be given access to GPUs. So Stevens Institute for AI and the lab for AI and mathematics education, they gave me access to GPUs. And then I was like, all right, let's just run this and see what happens. Once we had that computational power, we just found tons. It was running it, come back, get a coffee, come back a few hours later, and it's just like, oh, I found 27,000 counterexamples. Like, huh? Yeah.
When you find something,
yeah,
is it in the optimization phase that is yours, or is it in the suggested new ones from the machine?
Great. So great question. So both.
Both.
Both. Oh. Yes. We also immediately began finding counterexamples that had virtually no resemblance at all to the one that I showed you previously. In fact, we ultimately found hundreds of thousands of counterexamples to the strong tree unimodality conjecture across vertex sizes from 26 to 101. One of our greatest successes was with 60 vertices. In this case, the machine ultimately found tens of thousands of unique counterexamples. A histogram plot of our findings in this case can be seen here. Now, this histogram is not going to look like any histogram you've ever seen. What's going on here? Okay, so what's going on here? Notice how long the x-axis is, despite it seeming like there's nothing on the y-axis. There is something on the y-axis. The problem is that it's one. Okay, so we found counterexamples all along this, but each one was only ever found in one. Okay. And then there's this huge spike here. Does anybody want to guess what this huge spike is here, which it's hard to tell, but it's slightly to the left of 0. So this is the path.
A quick question.
Yeah.
So it's outputting still labeled trees.
Yes, correct. It's outputting proof. Yeah.
Okay.
Which the someone's labeled. Yeah.
That's why this one counts.
But what I'm saying is like these are unique updates.
Yeah.
Yeah.
Oh, so the one all across, those are unique.
Yes.
Oh, okay.
Yeah. Oh yeah. To be clear, it's like it rarely found the same tree like isomorphism. It rarely found the same tree more than once.
You're taking care of the relabeling to know if they are the same or not.
Well, the thing is like if it only finds the score once, that has to be. Does that make sense?
Yeah.
Because like the labeling does not affect the score function at all. So if it only finds the score once, you know for a fact that it's the same tree. And indeed, in this case, it was pretty much it's just one, right? It found all the positive examples once, and then it just was like, I'm just going to chill with the path. And because
the path is easy to optimize.
So this is a great question. We don't have a good, we really do not have a good explanation for it, because as I showed at the beginning, like the path absolutely can be optimized with my optimization algorithm. 100%. Like that, I drew an example where I started with the path and I ended with something that's not the path, right? It can be optimized. The machine didn't seem to care. It's just like, okay, user, here's 100,000 new samples, and like 40,000 of them would just be the path, but relabeled, right? Like it did not output like the exact same path. It would output the path, but with different labels.
But it's knowing that that's what you're doing. Like part of the cycle is that you're optimizing.
Yeah.
It's giving you something that you can easily optimize.
So I see. So it's like here. So it knows that the path is a good starting place for the output. Yeah. So absolutely, that's possible.
So also what's manifesting over there is that as n grows, the number of non-isomorphic trees reduces, right? So most of them are unique.
Yes. Yeah. All right, so one should glean a few things. First of all, of the many positive scores, each appeared very few times. In other words, it was rare for any counterexample to be found more than once. Secondly, there's a rather conspicuous spike just before the score of 0. This turns out to be the machine finding many relabelings of the path graph over and over again. This is the second time we've seen this. Indeed, it was a strange quirk that it would, at all vertex counts, to be clear, it wasn't like, oh, this was less prevalent as n got bigger. Look, at all vertex counts, became fixated on the path graph if you ran PatternBoost for enough generation. We still don't have any formal explanation, but this idea that it zoned in on the path as being a good starting point for optimization, maybe, definitely. That's a great thing that I actually have never thought of before. But otherwise, yeah, we don't have any formal explanation for why this happened. So here's some examples. So, or rather, examples of counterexamples. So here's one on 60 vertices. The breakage happens at the index 30. There's its independence polynomial. There's its Cooper code if you're interested. Here's another one. Again, diverging pretty significantly from that very standard form that the original counter. Here's one on 67 vertices. Lots of subdivisions, right? Lots of degrees of vertices. Which, incidentally, like for random graphologists, like the number of degree 2 vertices is something that you expect to be growing, right, as n goes. Breakage at n over 2. Yes. So to be clear, when I say n over 2, I take the floor n is on. Yeah. So.
But all the examples.
Yes, breakage at n over 2, and I'll get to that. Here's another one on 67 vertices. Now, in terms of the scores, let me just say, so we found scores ranging on the large end from like 10 to the 10th. And on the small end, we actually did find a tree whose score was 1. So it's the least non-log-concave tree possible, right? The score was 1. It was the smallest possible positive score. So yeah, okay. So to end today, I just want to discuss some interesting kind of failures and limitations of this approach. So to start, our methods had a very hard time of finding examples of breakage away from half the number of vertices on the nodes. In all experiments where we looked at breakage at an index that was not n over 2, the transformer defaulted to just printing the path after about 5 generations. So the following histogram shows the output of the transformer generation over generation when we looked for breakage at n over 2 minus 1 with n is equal to 56. Now, one of the Galvin examples does have this breakage at n is equal to 56. The point is we knew from previous literature that there do exist counterexamples here. And so here's the histogram there. So it starts, it's like more or less random. The path somehow appears twice again. And then, okay, so notice that this is 10 to the 17th. And here, this is 10 to the 11th. So like, even though the histogram is kind of hiding it, things are moving pretty significantly towards the right. And then we move even more towards the right, more towards the right. And then eventually, in the 5th generation, it was basically just like, all right, I'm lazy, path, and this one. And this thing was the path with 1 extra kind of leaf added to the bottom. So it was like working, and like, you could tell, like, somehow the machine got lazy. Like, seriously, it's like trying so hard, and it's like ultimately diminishing returns, right? It knocked off 10 to the 17th to 10 to the 11th. Okay, that's pretty good. 10 to the 11th to 10 to the 9th. Okay, 10 to the 9th to 10 to the 8th. And it's like the improvements are getting not as good. And then eventually it's just like, half. Yeah.
So,
Yes, to be clear. All of it never got close to 0. So the fix to this issue is perhaps the most obvious one. So we've redefined our scoring function to assign a score of negative infinity to the path. So actively punish the machine, just like it comes like, here's the path. You know, it's like, no, try again, be better. Okay. So after making this change to our scoring function, the transformer no longer became fixated on any particular tree. Moreover, we found our first counterexamples with breakage away from n over 2. So here is an example This is at n over 2 minus 1, right? 56, n over 2 would be 28, but the breakage is happening at 27. And this is what the tree looks like here. And indeed, I believe, if I'm not mistaken, I do think we did. I do think we found those counterexamples of Galvin that were known previously as well. So we did rediscover the known counterexamples, and we found new counterexamples kind of at this point. So I will say that even after fixing this issue with the path graph, we still have not been able to find counterexamples where the breakage happens anywhere else with these methods. The reason for this is captured by the following conjecture that we arrived at through our extrapolation. So let T be a tree on n vertices which experiences breakage of log-concavity at the index n over 2 minus beta, where beta greater than or equal to 0 is an integer. Then the independence number of T is at least n over 2 plus beta plus 1. Again, when I say n over 2, if n is odd, take the floor. So, in other words, the further away from the top of the sequence that I'm looking for the breakage, the bigger that the independence number has to be to somehow compensate for that.
I didn't understand that.
Yeah, so like, again, the further away from n over 2 that I'm looking for breakage,
Okay.
the larger the independence number has to be to compensate. So if I want to find breakage at n over 2 minus 3, my independence number needs to be at least n over 2 plus 4.
Do you mean n plus beta plus 1 or n over 2?
N over 2. Remember the independence, so the independence number,
It's the largest.
the independence number is the size of the largest independent set, yes. And for trees, it's going to be between n over 2 and n minus 1. Okay. Now, generically, like if you take a random labeled tree, alpha is going to be approximately 67% of it with high probability. So, like when you think of the independence number, like this is kind of the range you want where it lives, alpha here. Okay, so I say that this conjecture explains to a certain extent why our machine was having a harder and harder time, and it's like, why does this imply that our machine is going to have a harder and harder time? Well, once you think about this, yeah. Here. Why is this related to the failure of our machine agent? So one of the most interesting behaviors that our machine displayed was an insistence rather on producing examples with the smallest possible independence number. It did this every time, and only after 1 or 2 generations it would exclusively produce samples whose independence number was between n over 2 and n over 2 plus 2. So like pretty much, and again, remember, generically my independence number is about 67% of n. So it's not like, oh, it's regressing to the mean, right? For some reason, the machine started exclusively producing things with small independence numbers, like really quickly, which is impressive because, again, if you just handed me a proof of code and you asked me what is the independence number of this tree, I wouldn't know. If you were to hand me a proof of code and be like, hey, could you, or rather, if you were to just be like, hey, could you give me a proof of code with small independence number, I wouldn't know how to do that. Like, I don't know exactly how the machine got so good at doing that. Note that for theoretical reasons, as I was saying, the expected independence number of a randomly selected little tree is about 0.67n. And so this behavior is not just regression to the mean. We don't know why it's doing it. We don't know how it's doing this. Now,
Is it true that if there's breakage, asymptotically, it has to be at n over 2?
So, no.
Asymptotically.
No, so how do I answer? I think like the breakage that's happening in, for instance, the newest like Bautista Ramos examples, it is not asymptotically at n over 2. The original, again, going into this project, everything that was known was either n over 2 or asymptotically n over 2, but I think that's no longer the case. I think we have more examples.
And this behavior even happened after you defined
Yes.
major provision.
Yes.
So you were not able to find examples other than n over 2?
No. We got n over 2 minus 1 as well.
No, I know, but like away from n, like really. like asymptotically not.
No. Yeah. So in this project, we ultimately only got counterexamples where breakage was at n/2 or n/2 minus 1. Yeah. And again, assuming the previous conjecture, it's like if you want to find breakages that's like really far from n/2, then you need independence numbers that are like quite larger to compensate for that. But the machine, again, consistently kept producing trees where the independence number was as small as possible. It just started doing that, and so.
What if you change your optimization algorithm to improve a different index, not the middle one?
Yeah. So if you take the scoring function that we started with and you choose any other index, well, before we did the negative infinity score for the path, after about maybe 5 generations, the machine would exclusively print out the path, right? If you looked at anything that was not n/2, the machine would basically give up in 5 generations, just keep printing the path. When we assigned like negative infinity to the path, it wouldn't do that anymore, but it wouldn't really make progress. It would just kind of like walk in circles, and it did not look like it was converging on anything. It would just get lost. Yeah.
Have we considered adding the independence number into your scoring function?
So this is an excellent point. So when we first started, again, we were on local machines, and our first scoring function did incorporate the independence number like that. And those first experiments were like complete failures. So we put it to the side and we changed our focus to look at n/2 again, because at the time we're like, we know there are counterexamples at this index. So why don't we just, first thing we're going to do is we're going to find the counterexamples we already know, and then hope from there we can expand and get new tests, right? And then, as I said, we did this and we were just like printing counterexamples, and it was just like, oh my god, look at all these counterexamples. There's so many counterexamples, and I'm just like, I'm so happy with this, right? And so we finished the project and did not come back to this idea about incorporating the independence number into the scoring function, right? And then a couple weeks ago, maybe a month ago, Greta, Panova, Steve Heilman put out a paper where they used a kind of modification of our code to do the same exact thing for dominance numbers. And they were wildly successful, and in their paper, they did incorporate the dominance number into the scoring function they were using. So what I will say is that very likely what happened here is, like, again, it was an artifact of us working on local machines at the beginning, that the scoring function using independence numbers was not as successful, but that's because our computations were not as successful, or rather our computers were not as powerful. And it is possible, and in fact, probably quite likely, if we were to redo this, now that we have access to GPUs and stuff, probably we should have stuck with the original idea. Yeah. So, and indeed, like, to be clear, there is a follow-up project like in progress right now. I'm working with Francois Charton, and we're doing this, but like improving a lot of aspects of it. For instance, we are not using PatternBoost. We are using PatternBoost 2. Which I insisted he called 2 pattern 2 boost. But I don't think he got the joke, and he's like, no, it's called Explorer, because the company he works for is Axiom, and so it's Explorer, and it's PatternBoost 2, and it's considerably better than PatternBoost 1. Like, all of the background machine learning stuff has been optimized within an inch of its life, and now it's like, oh, this runs actually really well on CPUs. You don't even need GPUs for certain computations. But we're working on that, and as part of it, we are definitely changing the scoring function. For instance, targeting a specific index, you might notice, is probably not going to help when it comes to the original unimodality conjecture, right? Because unimodality is more like you need to see a bell curve type thing, which is kind of more of a global shape than looking at individual points. Anyways, so yes, this is all stuff that is in progress for the follow-up. Yeah, just as a note, obviously the path has the smallest possible independence number for a tree, so it's possible these two phenomena are somehow related to each other, but I don't really have anything intelligent to say that. So another unexpected problem. So PatternBoost, the machine learning is happening in Python, okay? But the local optimization, again, this is PatternBoost, has to be coded in Julia. Because Julia is just slightly better at doing computation than Python. Now, one quirk about Julia that Python doesn't have is that Julia's integers only go up to 2 to the 64. Once you get above 2 to the 64, they integer overflow. So you need to use this data type called bigint. And bigint sucks. I mean, bigint is like, you give me 2 bigints and you're like, hey, could you literally add these 2 bigints to each other, and Julia literally you'll blink and the computation won't be over. It's like, how could you lose that much efficiency? It's crazy. Bigints are bad. So this slows down everything to the point of not really being viable. This was one of the perks of PatternBoost 2, which is that they did everything in Python this time. They did not go through Julia at all. But anyways, so once you get above 66 vertices, the numbers involved get so big that you need to use bigints. And so here is an example of a tree, a counterexample with 101 vertices. These numbers are really big. But it ties in with kind of a funny story that's somewhat remarkable, which I always end this talk by saying, which is that, okay, so we're coming along, we're printing counterexamples, we're finding all of these cool phenomenons, we're like doing really great. And I'm like, I'm feeling confident. And I'm like, you know what? Let's just push this to 101 vertices. Let's go. So I'm like, I go into my code, I set the number of vertices to 101, I run it, I step away, come back a few hours later. And PatternBoost, I look at the most recent outputs and they found a counterexample. Maybe I just and it found a counterexample, and I'm like, oh, that's so wonderful. Let me see what its independence polynomial is. So I compute the independence polynomial, and I am shocked to find that this tree has negative 500 million independent sets of size 26. And I'm like, well, the first thing that came to my mind is like, this is how I'm going to win a Fields medal. By discovering a tree with a negative number of independent sets. Blow everybody's mind. And then immediately I'm like, wait, no, that's wrong. So I stopped PatternBoost and I'm like, oh my goodness, I had no idea that Julia has this restriction. And even if I did have an idea that it has this restriction, I guess I'm just not experienced enough to worry about integer overflow. So I go in, I create a new file on the side, which is the exact same file but uses bigint instead of integers. I run it, I come back. Now, back then, the 2 or 3 generations that had run only took like 3 or 4 hours. Once I changed everything to bigint, the 2 or 3 generations took something like 30 hours to run, just to give you a sense of how much longer it takes with bigint. And counterexample, wonderful. And it's the exact same tree. So even though in the previous setting, like there was integer overflow happening everywhere in the middle of this polynomial. These were all negative. All of these coefficients here were negative. Complete nonsense. The machine still found something, ultimately produced something here that was a counterexample to log-concavity. Now, okay, so you counter and you're like, okay, yeah. But notice that like the coefficient that I care about, which is the 50th one, is not nearly big enough for integer overflow, right? So like if my score is only really looking at these coefficients, there's no integer overflow happening, so maybe it's not so miraculous. And to a certain extent, that's true. But remember, the independence polynomial is computed like recursively, so you would expect, or at least I at the time expected, that to understand the independent sets of size 50, I have to have some understanding of the independent sets that are coming before. But in fact, it turns out you don't. Like somehow the machine does not care at all about what's happening in this section of the polynomial, and it is 100% only caring about these coefficients here without any concern for the smaller independent sets while it's doing it. Okay, I guess that's all I have to say. Thank you. Yeah.
Obviously, if you pick a random tree,
Yeah.
you're not going to get a counter example because
Yeah.
otherwise people would have found it by trial and error, right?
When you say random, do you mean like formally random, or just like I'm a human being and I threw points and arrows on a piece of
I
paper?
don't know, but let's say you have a way to generate trees, right? And not in any particular structured way.
Yeah.
And just try them out.
Yeah.
You know, I'm sure that's not going to lead anywhere.
Yeah.
I mean, not sure, almost
Sure,
sure,
sure.
because otherwise people would have discovered those by chance.
Sure. So certainly, I do not believe that being a counterexample is like a generic behavior. I don't think it's a probability one behavior, but I wouldn't be surprised if you told me that they have like a positive proportion, like a non-zero proportion.
Fine.
Yeah.
So my question is that, is there a way to generate trees in some weird way? And then, you know, like a family of trees, and check them until you find by chance the counter example.
So what you're describing, notice that if in my local phase here, I set the number of swaps to 0, okay? So my local does nothing. It literally takes in a tree, gives you back the same tree. Sends that to the machine gives you new, and then you effectively start with randomness and then just do nothing to it, and then like that procedure, again with no swaps, always the machine ended up converging on spitting on the path. So like all this to say is that like in our experiments, like if you just literally started looking at random trees, it did not seem to be conducive to finding large numbers. Yeah.
So here you get specific examples. Can you generalize the family from this? Yes, that would be one goal. I guess another question with that was, could the AI itself generalize the families of other AI?
Great. So PatternBoost specifically, like the transformer architecture there is not like designed to do that. Now, a question of whether I could take all of the hundreds of thousands or whatever examples we have, take that entire reservoir of samples, hand it to something like a large language, like one of these like ChatGPTs, DeepSeeks, and be like, hey, given all of this, can you see any patterns or generalized families? Possibly, I don't know. That's not something that we tried. But potentially, I suppose, like that might be interesting to see, like as a step 2 of this process, assuming all of what I said here is step 1, is like now I have a reservoir. Take this reservoir, take it to some kind of artificially intelligent machine agent and be like, here's a bunch of stuff. Can you observe any patterns? Can you give me a group of trees that you think is going to? Yeah, potentially that, you know, maybe there is something there, but it is not something that we've done. Yeah.
So I was thinking about that pattern on N/2.
Yeah.
So it's independent sets, right? So there are a lot of small ones, which is why it was exceeding
in the middle.
capabilities.
Yeah. The middle is kind of
probably when by the time it reached N/2 is when it became, the numbers became small. Did you check if there was any breakage after that?
So when you say breakage after what? Sorry.
So did the machine just stop when it found a breakage, or did you check all the breakages? Maybe after that there was some.
I see. So like, yes, in all the counterexamples we produced, just as like a due diligence thing, we did look at the independence polynomials and compute the scores at every index to see if we accidentally found something where breakage happened twice, and we never did. Mm-hmm. So like all of the examples that we produced through this experimentation ended up being single breakage examples at either N/2 or N/2 minus 1.
So this follow-up question. So independent sets, the independence number is the largest, right?
Yeah.
So domination number is the smallest.
Yes.
So was it reversed, like some?
It's not. So like in that paper, I believe they define the domination sequence instead of being AI, it's a n minus 1. They literally
Oh,
just
so
take
they-
the
Yeah.
fluidity out. So in that sense, they have the same.
So did they also get something like the N/2?
No, so for them, as I said, like in their experiments, they started on GPUs with the confidence of the fact that this definitely worked, and their scoring function was determined in terms of the domination number. So,
What is the domination?
so it is the smallest set of vertices for which every other vertex has a neighbor in that set. This is called the domination number.
And they use that somehow in the scoring of the.
Yes, but again, they were looking at the domination sequence. So if you define like AI to be the number of dominating
Oh,
sets
they
of side
changed
side.
the-
Yeah, the whole premise changed. They didn't literally work with that.
And this is not working for unimodality?
Right. So again, all examples that we were able to produce from this are still unimodal. Now I will say something in terms of like the unimodality. So just why does log-concavity imply unimodality? Well, if you are in a situation where you go up, down, and then up again, at that point where you go from down to up, log-concavity has to break, essentially. So this is why log-concavity implies unimodality. So in particular, if there were a tree that is a counterexample to unimodality, it would have to have log-concavity breakage. That's number one. Number two, it is known deterministically that the independent sequence of a tree is increasing for the first like 49.5%. And it is known deterministically that it is decreasing in the final third. Okay. So if there were an up, down, up situation, it would have to happen essentially between 50% of the independent sequence and 67% of the independent sequence. Okay? So you would need to find log-concavity breakage that happens in that range. But now this is why I was saying before it's like really important. It's like we thus far, with all of the papers that have been produced, we can only ever find breakage at a fixed distance from the top. Right? We can find it like for fixed K, you can give me a tree for which breakage happens at alpha minus K. And that is different from saying I can find breakage at like 67% of alpha. Right? Because the examples that are produced, always alpha is growing with the number of vertices. And so like that range is getting kind of further and further away. So, yeah. Oh, so I was just going to say, like, if unimodality fails, you would need to produce a tree for which log-concavity fails in that range between about 50% and 67% of the independent sequence. And all of our methods are not really getting there because all of our methods are only about the distance from the top of the sequence rather than proportion of it. Yeah.
And so for all graphs, it's known that it's not unimodal.
Yes, very much so.
And in Juna Hu's work, and like as you were mentioning that, do you know, were there any examples where they're able to prove where like it always unimodal but not log-concave? Or are there examples of that, like this kind of?
Right. So basically, like what's happening is if your sequence is secretly a sequence that is counting flats in a matroid, okay? Even non-realizable matroids, which in principle are fundamentally not geometric objects, still have geometry. This is June's, June and co-authors like field metal winning stuff, which is like you have a Hodge theory for matroids, and because of Hodge theory, oh hey look, punctured duality, so you get this like symmetry in the top and bottom and yada yada, right? So in June's work, it's like the idea that has come out of that work is that there is like a combinatorial geometry, and log-concavity is a reflection of that combinatorial geometry. Now, do there exist sequences which are not unimodal but are log-concave? Yes, of course, those do exist. But somehow, what that suggests is that unimodality is being caused by something that is in a ways not geometric, at least in how we understand. Like Hodge theory, maybe it's better than geometric.
So as soon as you have the Hodge theory, you have the log.
Yes, that's fair. I mean, there's like an old paper of Stanley where he's like, oh, unimodality suggests the existence of like an SL2, where SL2 is the scripted lowercase SL2, the Lie algebra SL2, action. There's like a representation theoretic interpretation.
That's
But-
the Hodge theory.
What?
That's the Hodge theory.
Not quite, because okay. Yes. From Stanley's perspective, like unimodality specifically is being caused by like a real. It's all that. SL specifically, it's SL2 action is like creating this unimodality phenomenon. The log-concavity is like a higher Hodge theory that is related with like matrix geometry. I suppose not getting into too much detail. But yeah, to summarize, we do not have great tools for unimodal but not log-concave. We genuinely don't, because like all of these wonderful things that June is doing actually do not apply. Okay.
Fantastic. Let me take the opportunity to thank John Cutler, the co-chair, and also Manasseh Lim, without whom this would not have happened. So, thank you. Oh, we have 2 more days, not going to end. Can I